Okay, so I thought I'd take a moment and explain the the empirical rule for statistics. So to do that, let me set this up a little bit. So first, the figure shows the values on the distribution of IQ scores from the example. So IQ scores are uh, normalized on purpose. They have a mean of 100. And because they're normalized to the mean, median, mode, it's all the same. So the IQ score has a mean of 100, and then it has a standard deviation of 16. So that means if I go down one standard deviation, then I'm going to 84. If I go up one standard deviation, I'm going to 116. That is one standard deviation. If I wanted to look at what a particular score was, I could do that using z-scores. We don't need to worry about that so much. I just wanted to kind of mention we can talk about ones that are not nice, like not right a standard deviation. Like 85 is negative 0.94 standard deviations. So it's not quite one, negative one. And a z-score or IQ score of 125 is up 1.56 standard deviations. But you'll notice we can see that most of our data, most of the results fall within 3 standard deviations, plus or minus, of our mean. And you can see that there's still a big chunk that's in two standard deviations. So that would be like here, and then one standard deviation, which still has quite a bit. But this creates what we call the empirical rule. And the empirical rule works something like this. It's a simple rule, and it's also called the 68, 95, 99.7 rule. And it gives precise guidelines for the percentage of data values that lie within 1, 2, 4, and 3 standard deviations of the mean for any normal distributed. So it has to be a normal distribution for this to work. And the great thing about it is we can say a lot about data very quickly if we know it's normally distributed and we know what the standard deviations are. So 68, 68% of the values fall within one standard deviation of the mean. So on our previous example, the 100 and the 84 and 116, that means that 68% of everyone who takes the IQ test, fall within 84 to 116. Almost everyone does. It also means that 95% is within 2 standard deviations. This means between 64 and 132, 95% of everyone who takes an IQ test falls between 68 and 132. And then 3 standard deviations is the 52 to 148. And that is 99.7 people who take the IQ test. So that's almost everyone. Fall within 52 to 148. That's what they score. So this is useful. We can use this to determine heights. We've talked about heights already. Heights are normally distributed. That's a very common tool that we use. So the heights of females are normally distributed. The heights of males are normally distributed. This means there's an equal number lower, equal number higher. And yes, because it's 99.7, you can still have outliers that are really short or really tall. But because of the fact that we're modeling heights, most people, so more than half of the females of a particular age, you'd have to block off an age. And it's usually something like 18 to, I don't know, 28 or something like that. It might be a little bit older than that, but right around there. 68% of everyone, all males or all females, fall within whatever the mean height is and one standard deviation above and below. 95 are within two standard deviations. So most people are in here, even more, so practically everyone. And then by the time you go 3 standard deviations, you're really including the general population. Not that there won't be outliers, just that there's not that many. So this is a very useful tool. So let's kind of formalize it. So it's about 68%, more precisely 68.3, but for everything that you guys use, just 68% works just fine. Okay, one standard deviation. 95, the precise measurement is 95.4. Again, for what you're doing, 95 will work fine. Of the data points fall within 2 standard deviations of the mean. And 99.7, yes, this one is precise. Of the data points fall within 3 standard deviations of the mean. Notice that this last one, 99.7, we don't round, whereas the other ones, they were rounded to the nearest whole number. We didn't round this to the nearest whole number because the nearest whole number, when we round this, is going to be 100%. And we hate to say everyone. We do know that there are some outliers. Now let's look at some other places where normal distribution happens. Normal distribution, I've mentioned before, happens when we talk about like people, heights, etc. We can use this to talk about trees. We can use this to talk about animals. Anything that's living usually has, depending on what we're measuring, usually has some form of normal distribution. And tests, most standardized tests that you take are standardized, which means they've been put to a normal distribution. So we're going to look at the SAT scores. Most of you took an SAT score. The tests that make up the verbal, critical reading, and the mathematics part of the SAT. And this is true of the GRE, which is what you use to get into your master's or doctorate programs. Your LSATs and your GMATs are designed so that their scores are normally distributed with a mean of 500. And we often use the mu, the Greek letter mu, which is what you see there, equal to 500, and a standard deviation of sigma, which is equal to 100. And it's asked to interpret this statement. Well, if we're interpreting the statement, we can start very simply with the fact that using that empirical rule, the 68% of the students have scores within one standard deviation. Because the standard deviation is 100, that's a plus or minus 100 from 500. So that is 68% of students score between 400 and 600. Also, 95% of the students score within 2 standard deviations, which in our case would be 200 now, of the mean of 500. So that would be 300 to 700 students. 95% of students score between 300 and 700 on the SAT scores. And about 99.7% of the students score between 200 and 800, because that is 3 standard deviations, or 300 plus or minus the 500. So added to 500 and subtracted from 500. And that gives us the 200 to 800. So that's pretty powerful to say. This basically says exactly what I just said, but let's look at what this looks like maybe as a picture. So we have our normal curve, and we can see the pattern of this going across. And that's pretty powerful. It's pretty neat. We can use these properties to help tell a lot of information. Like, I could tell how many people are going to score below 600 or below from this information. I have the 600, that's one standard deviation. And I know because this is normal, that my 500, half of the data is above and half of the data is below. I also know that 400 to 600 is 68% of the data. So if I took half of the 68, I would have 34. And so that means that 34, let's see if I can do this. That means from here, let's go a little lower, to here is 34. But also to here is 34. And these are percents. Harder to do without writing one. But I also know that from here all the way to the very end is 50%. Right? I know this is 50. Ooh. Okay, so 50 and 34 is 84. So from here down is 84%. So combining what we know about normal distribution, half the stuff is below, half the stuff is above, and then utilizing the 68-95, this rule right here, right? Or the empirical rule is what we call it. This can tell me almost from any point, that's a standard deviation. It can tell me about where all the data is. So this is a very useful technique. All right, I just wanted to get this out. Not sure if we're going to get to cover this, but I wanted you to have resources. All right, you guys, have a wonderful day. And I'll see all of you in class.